Chapter 15, entitled Acid-Base Titrations and pH. In this first section, where we're going to talk about aqueous solutions, and then and tomorrow then we'll talk about the concept of pH, how we describe how concentrated an acid or how strong an acid or a base is. So what we want to accomplish in this section, we're going to describe something called the self-ionization of water. Water is going to ionize itself. Then we're going to get on to the section tomorrow where we're going to talk about pH and how we can calculate that. In this section, we'll just talk about whether it's an acid, a base, or if it's neutral. And then we're going to tomorrow use the pH scale and determine the numbers that we use for that. And then we're going to in this section today, we're going to, if you're given the hydronium ion concentration, can you figure out the hydroxide, or vice versa? Tomorrow we'll take that and go one step farther and figure out the pH. And then flipping that around, if you've been given the pH, can you find the hydronium ion concentration or the hydroxide ion concentration? Now, in the self-ionization of water, we have two water molecules, and they're going to produce a hydronium ion and a hydroxide ion by the transfer of a proton. So this transfer of proton is going to happen. One water molecule is going to lose a proton, the other one's going to gain it. So here are the two water molecules there on the left. We have H2O plus H2O. And one of those is going to donate a proton. So in other words, it's going to function as an acid. The other water molecule is going to accept that proton and function as a base. So as a result, we're going to end up with a hydronium ion, H3O plus, and a hydroxide ion. Now, notice in the middle that we have the arrows pointing in both directions. This is by no means completely ionized. In fact, it's just only slightly ionized, but it does happen, and it is an important thing in our growing understanding of acids and bases. Now, in water that's at 25 degrees Celsius, that's around room temperature, the hydronium ion concentration in pure water that has self-ionized itself, that concentration of hydronium ion is around 1.0 times 10 to the minus 7 molar. Remember, that's the capital M stands for molar, moles per liter. And the hydroxide ion concentration is also 1.0 times 10 to the minus 7 molar. And as we look at the equation above, we know that when self-ionization occurs, we're getting an equal number of moles of hydronium ions as we do of hydroxide ions. So thus, the concentration of these two in pure water will be exactly the same. And so this brings us to something new that's called the ionization constant of water. This is a number you will need to memorize. It's not a difficult one. And that relationship, the ionization constant of water, the Kw, we're going to call it, the Kw for water is equal to the product of the hydronium ion concentration and the hydroxide ion concentration. And this equation will be true whether we're talking about pure water, we're talking about an acid, we're talking about a base. We'll use the same equation for both. So the ionization constant of water is just the product of the two. So and we'll kind of work with that a little bit more. So at 25 degrees, we know that the concentration of the hydronium ion, and notice again that we maybe have forgotten this, that when we put H3O plus in brackets in this situation, we're talking about its concentration. So it'll be 1.0 times 10 to the minus 7 molar, technically, moles per liter. And then the second number there, the hydroxide ion concentration is also 1.0 times 10 to the minus 7. So if you took your calculator out and multiplied those two numbers, you'd come up with 1.0 times 10 to the minus 14. So it's just a product of those two. The Kw, or the ionization constant of water, actually increases as temperature increases. So if we were doing this under different temperature conditions, we would probably have to use different numbers, but since most of our experiments can be done at room temperature, we can just memorize the one number, 1.0 times 10 to the minus 14. Now, in solutions in which the two concentrations are equal to each other, they're neither acid nor base, and we refer to them as being neutral. So the two concentrations are equal when the solution is neutral. A solution in which the hydronium ion concentration is greater than the hydroxide ion concentration is considered acidic. It's acid-like. And here would be a way of representing that mathematically. The hydronium ion concentration, the H3O plus in brackets, is greater than 1.0 times 10 to the minus 7 molar. So anytime that concentration is more than that, it's going to be acidic. In basic solutions, the hydroxide ion concentration is going to be greater than the hydronium ion concentration. Hydroxide ion concentration greater than the hydronium ion concentration, or written mathematically, the hydroxide ion concentration is greater than 1.0 times 10 to the minus 7 molar. So if the OH concentration, the hydroxide ion concentration is greater than 1.0 times 10 to the minus 7 molar, then it's going to be basic. If the hydronium ion concentration is greater than 1.0 times 10 to the minus 7 molar, then it's going to be acidic. Strong acids and bases are considered completely ionized or dissociated when we put them in weak aqueous solutions. This is something, a carryover from previous chapters. As long as they're not too concentrated, a strong acid or a strong base will completely ionize or dissociate. So let's take a base like sodium hydroxide. Notice it's the Arrhenius base. It has an OH in it. And when we put it into water, it will dissociate into a sodium ion and a hydroxide ion. And the equation is balanced, so that means for every 1 mole of sodium hydroxide, I'm going to get 1 mole of sodium ions and 1 mole of hydroxide ions. Now, let's suppose that we have a solution of sodium hydroxide that is 1.0 times 10 to the minus 2 molar. So instead of a whole mole per liter, we're only having 1.0 times 10 to the minus 2 moles per liter. And it has an OH concentration of 1.0 times 10 to the minus 2 molar. Now you might wonder, how did we get that number? Well, just remember in our basic equation there, for every 1 mole of sodium hydroxide, go way over to the right, the hydroxide ion concentration is 1 mole as well. They're in a 1-to-1 ratio. So if I have 1.0 times 10 to the minus 2 molar sodium hydroxide, I'm going to have a hydroxide ion concentration of that same number, 1.0 times 10 to the minus 2. The hydronium ion concentration of this solution has to be calculated. There's nothing in that that says what it is directly, so we have to calculate it. But we know what Kw is. Kw is at 1 times 10 to the minus 14. So taking our equation that I said we would use in every kind of solution of acids and bases and water as well, the Kw is equal to the hydronium ion concentration times the hydroxide ion concentration. And we know that the Kw is equal to 1.0 times 10 to the minus 14. So If I were to solve our basic equation for the hydronium ion concentration, I would have to divide both sides by the hydroxide ion concentration. So I'd have Kw divided by the hydroxide ion concentration. And Kw is equal to 1.0 times 10 to the minus 14. So 1.0 times 10 to the minus 14 is being divided by the hydroxide ion concentration, which we have there in the middle of the page, 1.0 times 10 to the minus 2 molar. So 1.0 times 10 to the minus 14 divided by 1.0 times 10 to the minus 2 is equal to 1.0 times 10 to the minus 12 molar. I would strongly suggest that at this point you stop the video and you take out your calculator and practice putting in numbers in scientific notation, making sure that you get 1.0 times 10 to the minus 2 molar. If the hydronium ion concentration of the solution is known, it's different than the one we just did. The one we just did, we knew the hydroxide ion concentration. But let's say this time we know the hydronium ion concentration. Well, then the hydroxide ion concentration can be calculated using the Kw as well. So let's say we have a hydrochloric acid solution, HCl, and the concentration of this solution is 1.0 times 10 to the minus 4 molar. And if we were to write out the ionization of HCl, we would realize that for every one HCl, I'm getting one hydronium ion and one chloride ion. So they're all in a 1 to 1 ratio. So whatever the concentration of HCl is, the hydronium ion concentration is the same. So it'll be 2.0 times 10 to the minus 4 molar. So putting it into our basic equation again, where Kw is equal to 1.0 times 10 to the minus 14, and this time solving for the hydroxide ion concentration. So to do that, I would need to divide both sides by the hydronium ion concentration. I'd have to divide by the H3O plus concentration. And I'm going to have the OH negative concentration is equal to the Kw, which is 1.0 times 10 to the minus 14, divided by the hydronium ion concentration, which we have above here at 2.0 times 10 to the minus 4. So 1.0 times 10 to the minus 14 divided by 2.0 times 10 to the minus 4, and we'll come up with 5.0 times 10 to the minus 11 molar. That's the hydroxide ion concentration. Again, I would suggest that you stop the video at this point and practice your calculator skills to make sure that you're getting this same number. Because if you're not, it's only going to get worse. Now, here are some strong acids and strong bases and the acid concentrations. You can see on the left we have increasing acid strength toward the top. Down the bottom it says conjugate acid, and on the bottom it says base. On the right side it's conjugate bases at the top. So if you remember from our last chapter about acids and conjugate bases go together, and bases and conjugate acids go together. So notice that on the bottom we have conjugate acid and base together. On the top we have acid and conjugate base together. So here are some different solutions that and the hydronium concentration and the hydroxide ion concentration, and then on the right is the product. When you multiply the hydronium ion concentration and the hydroxide ion concentration, you'll notice that it's always 1.0 times 10 to the minus 14. So let's say we have a strong acid, and it says that it's the second one down under pure water. It says 0.10 molar. Okay, so that means that the hydronium ion concentration is going to be the same, 1.0 times 10 to the minus 1. And if I solve for the hydroxide ion concentration, I will notice that it's 1.0 times 10 to the minus 13. All I would do to solve for that second number is take 1.0 times 10 to the minus 14 divided by 1.0 times 10 to the minus 1, and I'll get 1.0 times 10 to the minus 13. And so as you go down this chart, you can try different combinations, but you'll notice that the product of the hydronium ion concentration and the hydroxide concentration is always 1.0 times 10 to the minus 14. And as you go at the top, we notice that we have the hydronium ion concentration that's greater than 1.0 times 10 to the minus 7, so they're called acids. But as you go down toward the bottom, you'll notice that it now, with the strong base, we have numbers that are less than 1.0 times 10 to the minus 7. Except for the one where it talks about strong acid, but the others, notice that it's less than 1.0 times 10 to the minus 7. But the strong acid in there, the 2.5 times 10 to the minus 2, is kind of a nice one to do with the calculator to realize that it still works the same way as it always has. Okay, so let's practice what we've just learned. We have a solution of nitric acid. It's a 1.0 times 10 to the minus 4 molar solution of nitric acid, so it's not very concentrated. Has been prepared for a laboratory experiment. And we're going to calculate the hydronium ion concentration for this solution. And then we're also going to calculate the hydroxide ion concentration for that solution. So we've been given the concentration of the solution is 1.0 times 10 to the minus 4 molar of nitric acid. Our unknown is the hydronium ion concentration, and as well as our hydroxide ion concentration. So what's our solution? Well, we know that nitric acid is a strong acid, so it will completely ionize. And when it ionizes, here is the equation for the ionization of nitric acid. Notice that when it ionizes, it's essentially reacting with water. The nitric acid, the HNO3, is going to donate its proton to water, forming the H3O+, and what remains of the nitric acid will be an NO3 negative that we see over on the right. And this equation is balanced, so that means for every 1 mole of HNO3, I get 1 mole of H3O+ and 1 mole of NO3 negative. They're all in a 1-to-1 ratio. So for every 1 mole of HNO3, I need 1 mole of water, but I'll form 1 mole of hydronium ions and 1 mole of nitrate ions. And if you remember this definition that we've had from a previous chapter, the molarity is moles per liter. So the molarity of HNO3 is really just the number of moles of HNO3, nitric acid in solution. So if we were to take the moles of HNO3 per liter and multiply it by the mole ratio, they're in a 1-to-1 ratio between H3O+ and HNO3, I will end up with moles of hydronium ions per liter of solution. So that will give us the molarity of the H3O+. They gave us the concentration of the acid. Now by doing this, we'll end up with the concentration of the hydronium ion. And we know that the H3O plus, the hydronium ion concentration, times the OH negative, the hydroxide ion concentration, that product is always 1.0 times 10 to the minus 14. So we can figure out the OH negative concentration by doing nothing more than taking my answer to A and dividing 1.0 times 10 to the minus 14 by that answer. So if our concentration of the acid is 1.0 times 10 to the minus 4, and our mole ratio we said was 1 to 1, then we will end up with 1.0 times 10 to the minus 4 moles of hydronium ions per liter of solution. So that means our concentration of H3O plus is 1.0 times 10 to the minus 4. So that's our answer to A. All we have left to do is find out the hydroxide ion concentration for B. And we're going to take this Kw equals the hydronium ion concentration times the hydroxide ion concentration and solve for OH. The OH negative is going to be 1.0 times 10 to the minus 14 divided by the hydronium ion concentration, which is 1.0 times 10 to the minus 4. And my answer is 1.0 times 10 to the minus 10 molar. That's the concentration of the hydroxide ion. The 1.0 times 10 to the minus 4 molar is the hydronium ion concentration. And that's the far as we'll go for today.